Resolving occlusion in augmented reality. The following demonstration is running on a 2-processor Silicon Graphics Onyx with a Reality Engine 2. Since occlusion is an important visual cue, augmented reality systems need to address it when augmenting the real world with 3-dimensional data. We resolve occlusion between real and virtual objects by calculating depth values for each pixel in a pair of stereo video images using a new stereo matching algorithm. We write the calculated z-values into the z-buffer so that when the virtual sphere is rendered, it occludes and is occluded by areas in the image. Here we combine the left video image with a virtual sphere. Depth values are calculated only once, thus the shown update speed is only limited by rendering and by z-value transfer between main memory and the z-buffer. In this section, we recalculate the depth values with each redraw of the sphere to demonstrate the speed of the algorithm. By sampling at half the resolution of the image, we achieve an update rate of roughly 2 frames per second. The resolution of the algorithm can be changed to produce faster results. However, the accuracy of the results will be diminished. At 1/4 of the resolution of the image, the update rate is about 7 frames per second. We set up 2 video cameras, shown here, that feed into the Cirrus video card to transmit video images to our program in real time. Again, we display the left camera image on the screen with the virtual sphere. Our algorithm does not require the environment to be static because the depth values are recalculated for each pair of images.
The Nano Manipulator project is a collaboration between the Computer Science and Physics departments of UNC Chapel Hill and the Chemistry department of UCLA. The Nano Manipulator provides immersive and virtual window environments within which physicists may interact directly and in real time with materials a billionth the size of everyday objects. The user may explore and manipulate on the nanometer scale with simple gestures, remotely operating either a scanning tunneling microscope or an atomic force microscope over the Ethernet. In the Nano Manipulator's virtual environment, an image of the sample is presented as a 3D surface floating in space with the user. A force feedback device allows modifications to the surface to be felt, even as they are performed. New tools are introduced as a response to the developing skills and needs of the users, in combination with analysis of results. Tools include display controls to orient and scale the surface, as well as adjust lighting to bring out features of interest. Quantitative tools measure features and display scale, as well as record forces applied by the microscope. In this sequence, a virtual whisk broom is used to coax a segment of tobacco mosaic virus into position. The AFM tip oscillates between the 2 endpoints, whose separation and orientation are controlled by the user's hand. Markers appear showing the borders of the path swept out as the virus is rotated. The Nano Manipulator allows the user to develop manipulation skills using sight, touch, and hearing to perform intricate tasks on a minute scale. As this 15 nanometer diameter colloidal gold ball is maneuvered into a gap in a wire which had been machined previously from a 15 nanometer thick gold film on mica substrate, the user can feel the ball on the edge of the tip. The manipulation process is not well enough understood to be automated. Movement of the ball is unpredictable, requiring skill and tactile feedback to compensate for the erratic response of the ball. This user's delicate touch allows the ball to be pushed selectively through the region without damaging the wire or disturbing other objects in the area. These same tools and techniques are being developed and applied to a number of areas requiring interaction in the nanometer regime. Manipulation and fabrication become faster, simpler, and more clear in this virtual environment, which permits operations that are not feasible in commercial scanning microscopes. The nanomanipulator, by bringing the power of the user's faculties to bear in real time, is helping lift scanning probe microscopy to its full potential.
Most mechanical parts are designed to be used in assemblies or mechanisms and not alone. This is a demonstration of a system to help a user design and model mechanical assemblies. This system was implemented under Alpha 1, which is an ongoing research project into geometric modeling and manufacturing. This is the assembly planning tool. Before any geometry is modeled, a designer has in mind the object he wishes to create and its major components. The tree represents the breakdown of the assembly. Internal nodes are subassemblies, and the nodes at the leaves are parts, or subassemblies which have not yet been broken down. We can design top-down, bottom-up, or use a combination of these methods. Each component in the tree has an information box. On the left is a text documentation area for notes about the component. Next to it is a sketching area with several simple drawing tools to support the designer as he thinks. On the right is a geometry area. Once a component has been modeled, its geometry can be read from a file into this area. The design can be saved to a file. We can later come back to a design and revise it if we wish. This tool takes the assembly description and allows the designer to specify how parts connect to each other. The subassemblies are presented as specified in the planner. Small windows on the right contain the components of the current subassembly. The components are connected by specially defined assembly features. Defined features include surfaces, dovetails, pegs, holes, and others. If interference analysis shows that a part's geometry is not quite correct, the part can be redesigned and the new geometry substituted in. Degrees of freedom of a component can be examined at any time. Arrows indicate all the directions in which the selected part can currently move. Adding or removing other parts changes the degrees of freedom. The subassembly generated in a previous step is treated as a single component now for the purposes of the higher level subassembly. This allows us to create large assemblies without having to worry about too many components at any given step. Creating exploded views is useful both for creating documentation about an assembly and also for visually analyzing a completed assembly. The exploded view utility allows us to create an exploded view automatically from the known assembly information. When a new assembly is read, the program generates an exploded view at just the top level. Components are not exploded. On the right, there are small windows representing the current subassembly, its parent, and its components. If any component is itself a subassembly, its name is shown in a push button. Pressing the push button causes that component to become current. Interactive controllers are provided for indicating whether a given component is visible and whether or not it is shown exploded. We can also interactively change the length of the blue leader lines which show where a component was exploded from. Likewise, the parts in the illustration can be labeled. Labels are view-dependent and placed so as not to interfere with components. Here is the main assembly fully exploded. We can now experiment with the view until we find one we like.
So how did you like that?
It looks nice. I think it synced up pretty well.
Do you think that worked for the conference?
Yeah, I think so.
Okay. I'll let you get back to Disney.
Okay.
See ya.
Thanks, Jim.
No problem.
This video will demonstrate how wavelets can be used for hierarchical and variational geometric modeling. First, we will show wavelets being used for hierarchical curve modeling. In a control point scheme, the user defines the curve by dragging around a set of control points. Using wavelet analysis, we can obtain a multi-resolution representation of the curve and allow the user to manipulate it at any desired resolution level. Here we see the user manipulating the curve at a coarse level, changing the broad overall sweep of the curve. Now we see the user adding in detail at a finer resolution level. In a least squared scheme, the user directly manipulates the curve using interpolation and tangent constraints, and the modeling tool returns the curve that meets the constraints by changing the control parameters by the least squared amount. Here we see the user using an interpolation constraint to manipulate the curve at a fine level. Now the user is using the same interpolation constraint to manipulate the curve at a coarser level. Now we will show how wavelets may be used to efficiently solve variational modeling problems. First, we will show what happens when an optimization problem is stated in a cubic B-spline basis with 65 control points. Because the problem is ill-conditioned when stated in the B-spline basis, many iterations are required for the solution to converge. Once the optimal curve has been found, there is enough information available to interactively move the constraint without resolving the optimization problem, and the constraint is therefore marked blue. The yellow dots show the 65 B-spline control points. The user has now moved the Miller constraint, setting up a new optimization problem. The B-spline problem is ill-conditioned because each of the B-spline basis functions represent only a very narrow region of the solution, and therefore information must propagate slowly from basis function to basis function. Variational problems can be solved quickly and the ill-conditioning avoided if the problem is stated instead in a wavelet basis. Because the wavelet basis is hierarchical, the solution method is able to quickly converge due to its ability to alter the curve at differing resolution levels. The user has now added a tangent constraint. Once the solution has been found, the user can interactively move this constraint using the delta information, and the constraint is marked blue. Of course, 65 is an arbitrary number of basis functions to be using. An adaptive method is needed to determine the degree of detail needed in the solution. This is easily done using a wavelet basis, because the magnitude of the wavelet coefficients indicate the degree of detail needed in each region. When the problem is simple, the program chooses a very small set of basis functions and the solution is found very rapidly. As the problem becomes more complicated, the program adaptively chooses more basis functions necessary for the solution. This allows the user to design a shape with any desired degree of detail. We have just seen three different solution methods: the B-spline basis, which gives rise to an ill-conditioned optimization problem, the wavelet basis, which can be solved more efficiently, and finally an adaptive wavelet method, which is able to dynamically adjust the problem size to fit the minimal answer. These ideas have been applied to surface modeling as well. Here we show a user using interpolation and tangent constraints to sculpt a surface with 81 degrees of freedom. The system starts off with the four corners pinned down with interpolation constraints. The user picks a new point on the surface and specifies a new interpolation constraint. The user now has added a tangent constraint at that point, freezing the current tangent directions. The user has just picked a new point, adding yet another interpolation constraint. The purple color of a box or arrow indicates valid delta information for that interpolation or tangent constraint. Now a new tangent direction has been specified at that point. The ability to directly manipulate and interact with a surface, instead of some control points and blending functions, provides the user with an intuitive interface. This direct manipulation requires the solution of a variational problem, and therefore it is important to find methods that can solve these optimization problems efficiently. The use of a wavelet basis is one such method.
The feature-based image metamorphosis technique described in a 1992 SIGGRAPH paper is shown here in an interactive implementation on a high-performance parallel graphics engine. The morphing process is controlled by means of line segment pairs used to establish correspondence between specific features in each of the two source images. Here we eliminate the undesirable fade-over area under the nose by adding line segment pairs between the nose and upper lip. Our system's interactive response makes it easy to quickly correct control parameters and test the modified morphing process. The fade-over area has now disappeared. Similarly easy and intuitive 2D techniques can be used to control shape metamorphosis of 3D objects, provided that they can be reversibly mapped onto a 2D surface. We demonstrate this on cylindrical projections such as those generated by some 3D scanner devices. Projected back onto the 3D geometry, the line segment pairs become surface-following curves. Without line segments, we observe uncontrolled blending of the two source models, the 3D equivalent of an image fade-over. Notice the double nose on the interpolated models. We add control segments to hold the mouth in place during the metamorphosis process. Interactive morphing now shows the mouth to be stable, but uncontrolled blending is still very noticeable in the eye region. We add a second pair of control segments to stabilize the left eyebrow. The eyebrow is now stable, but there is uncontrolled blending for the eye itself. We continue to add segment pairs to enforce controlled metamorphosis between various features of our models. In the graphics engine, the morphing is done on the cylindrical projection. The projection is then reversed and polygons are generated on the fly from the morphing data. Both morphing and polygon generation are done at user-selectable resolution. A low setting is used here for faster interactive response. Blending between the teeth and lower lip is eliminated by an additional control segment which forces the mouth to open during the metamorphosis. Only minutes into the interactive session, we have generated enough control data to display a convincing shape metamorphosis process between two complex 3D objects. Let's now examine the transformation process at the highest resolution. our frame rate drops to about 1 frame per second. We now lower the resolution again for higher frame rates. We have demonstrated interactive shape metamorphosis between complex 3D models with extensive local control over the transformation process.
This video demonstrates our algorithm to interactively render models composed of thousands of rational Bezier surfaces at interactive rates. We tessellate the Bezier surfaces into polygons depending on the current viewpoint of the user, and render these polygons using standard hardware. Notice how we can zoom in to parts of the model with no loss in smoothness. This is the wireframe rendering of the same model to demonstrate how the tessellation changes with view. To put our implementation in perspective, we compared it with the SGI-GL implementation of NURBS primitives. The rendering on the left uses our algorithm, and that on the right is the GL primitive. Both were rendered with the same sequence of viewpoints on a reality engine with one processor. We can improve the speed further using frame-to-frame coherence. The image does not change much between frames. This goblet model was designed using the Alpha 1 modeling system built at the University of Utah. This is another Alpha 1 model consisting of 576 rational Bezier surfaces. We get a speedup of almost 2 over the GL-NURBS primitive. With the exploitation of coherence, we get a speedup of about 7. This Alpha 1 model of a router has some trimmed surfaces, where parts of the full patches are cut out. Again, observe the effect of coherence. This is the Alpha 1 break hub, of which the previous router was a part. This sequence has been recorded off Pixel Planes 5 with 30 graphics processors and 10 rasterizers. Notice that we can maintain both smooth motion and smooth appearance of the model. This is a Splined Dragon and consists of more than 5,000 patches. This was designed as a hierarchical B-spline model, a scheme introduced by Force and Bartels in SIGGRAPH 1988. This rendering used 46 graphics processors and 16 rasterizers on Pixel Planes 5. Again, notice that we can maintain the smoothness of the model while rendering at interactive rates. This performance has led us to believe that online tessellation is the correct way to visualize curved surfaces. The complexity of the head in this model is much larger than the rest of the model. It has about half of the 5,000 patches. And it is this complexity that drives the overall rendering speed. And we can see the complexity of head by rendering different patches of the dragon in random colors. Look at the density of patches at the head.
This walkthrough of the Barcelona Pavilion was computed and recorded directly from a Silicon Graphics Reality Engine 2 workstation in real time. The scene is illuminated by direct sunlight, ambient skylight, and interior fluorescent lights. Shown here is the scene rendered with the linear color representations, preserving the light and surface spectral information. The shadows are cast by the direct sunlight and are implemented using projective textures. As we walk through the same path again, we toggle between the full spectral rendering and the corresponding RGB model. As we switch to the RGB model, note the reddish cast. The reddish cast is most prevalent on the ceilings and floors. Full spectral calculations capture the color information more accurately than the RGB model. Accurate color rendition is vital to applications such as architectural and industrial design. The linear color representations are particularly valuable when changing the spectral power distribution of the illumination. Because daylight can be reasonably represented with a small number of basis functions, we can simulate the transition from noon to dusk by simply changing the relative intensities of each of the basis functions. Now, we stop and change the time of day in an accelerated fashion. Lowering the position of the sun causes the shadows to move across the pavilion courtyard as we approach dusk. By extending the range of wavelengths over which they are defined, the full spectral light and surface representations naturally preserve the contributions of non-visible light. The RGB model, on the other hand, is strictly limited to contributions within the visible spectrum. For example, shown here is a scene containing fluorescent objects, which convert incoming ultraviolet energy into visible light. The spectral power of the illumination slowly varies from blue with a large ultraviolet component to orange with little ultraviolet light. The fluorescent contribution is toggled on and off. Observe that when fluorescence is enabled, the crowns are significantly brighter as the non-visible incoming spectral energy is being re-radiated as visible light. After pre-computing the surface representations, the computational cost is identical for the two cases. As in the previous example, this scene has been captured in real time. The full spectral representations also can be used in some cases where the spectral characteristics are a function of lighting and viewing geometry. Examples include Fresnel reflection from metals and thin film effects. For instance, shown here is the use of spherical environment maps to render thin film reflection. Because the maps preserve both geometric and color information, they capture the change in color as the incident angle of illumination varies. The optical thickness of the coating on the bust is varied smoothly using a stack of sphere maps in a three-dimensional texture. Again, this sequence is captured directly from the workstation in real time.
We simulate a 16-processor sort-first rendering architecture. This is our first example data set. We subdivide the screen into 16 regions. Each region is assigned to a unique processor. During the animation, we highlight primitives as they enter new screen regions. These are the primitives that would have to be communicated in a sort-first system. Non-highlighted primitives simply remain on the same processor from frame to frame. The gauges in the lower right tell us the following information. The green number is the number of primitives transformed. The red number is the number of primitives rendered to the screen. The green inner gauge shows the number of highlighted primitives as a percentage of the transformed primitives. The red outer gauge shows the number of highlighted primitives as a percentage of the rendered primitives. As you can see, taking advantage of frame-to-frame coherence allows one to greatly reduce the amount of communication necessary in a parallel graphics system. Let's see how this works for a more interesting data set. This is a model of the polio virus. The model consists of 50,000 spheres arranged in the shape of a dodecahedron. We have removed one of the faces of the molecule in order to see inside. Let's examine the surface of the molecule more carefully. A limitation of this example system is that it offers no means for load balancing. The processors assigned to the regions at the top of the screen have less work to do than the others. This is one of the major issues addressed in the paper. We can see that the fraction of primitives to be communicated still remains very small. Now let's take a look at a different kind of application. This is a walkthrough of a Radiosity shaded gallery. This dataset, courtesy of Cornell University, consists of 95,000 polygons. This application demonstrates the need to address another sort-first issue. What do you do with off-screen polygons? This topic is also addressed in the paper. One will note that the number of primitives to be communicated is relative to the speed of the viewpoint changes. While it seems that the animations shown are relatively slow, this is because of the overhead of the simulation. Let's see what this segment would look like at full speed without the simulation overhead.
goal of the ring system is to support real-time visual interaction between multiple users in a shared three-dimensional virtual environment. For instance, consider sharing a virtual environment with another user, who's shown on our screen as a yellow sphere with a green line for a nose. It is possible to interact visually with this other user. This system displays each of our movements on the other user's screen in real time. For instance, now the other user is spinning back and forth left and right, or moving forward and back. Likewise, our movement is displayed on the other user's screen in real time. Admittedly, only simple interactions are possible without collision detection and sound and other types of feedback. However, this is a research system, and visual interaction is adequate for the study of algorithms for maintaining consistent state between multiple users sharing a distributed virtual environment in real time. Let's now look at the same situation from a bird's eye view. Everything drawn from this view is the same as before. We're just looking down at the environment from the viewpoint in the sky. The walls and floors of the environment are still drawn, but with back faces removed. And we see a few more rooms from this viewpoint. The other user is still drawn as a yellow sphere. He's the one on the left side that's spinning back and forth right now. Our viewpoint is also drawn, but in addition to having a green nose, we also have a big purple view frustum that indicates our view direction. This view is used only for debugging purposes. It gives us a better way to track our user's viewpoint as we move through the model and to track what interactions are possible with other users. As we zoom back, we see the extent of the entire model. It's shown as this white box. This model is a maze of rooms that are connected by hallways. It has a total of 400 rooms and requires 23,000 polygons. I'm currently starting client programs on 12 other workstations around the network that are connected to our machine. These programs are creating 512 computer-controlled users that are going to interact with us in this virtual environment. In multi-user virtual environments this large, it's not practical for every participating workstation to process every update message from every user in real time. This video is being shot on a high-end Silicon Graphics workstation, and even it is dropping packets now because it cannot process them quickly enough. However, it's possible to use information about the three-dimensional geometry of the virtual environment. We can determine that most update messages are irrelevant to most receivers. Real-time update messages must be sent only to users that can perceive the effects of the change. In the ring system, client workstations with users communicate with each other via servers. Rather than blindly forwarding every update message to every other user, the servers use pre-computed spatial subdivision and line-of-sight visibility information to identify potentially visible sets efficiently, and then propagates update messages only to users in the potentially visible set. As a result, the network bandwidth into each client is reduced dramatically, by 95% in the situation shown here. Moreover, servers notify clients when entities enter and leave their potentially visible set, which allows clients to store and simulate behavior for a small subset of all entities at any one time. In the display shown here, all entities known to this client are being displayed and simulated every frame. When the entities appear or disappear, they are being added or removed from this client's list of relevant entities as dictated by the server. This client-server design allows us to build affordable multi-user virtual environment systems supporting many, many simultaneous users.
NPSnet, a multiplayer, three-dimensional virtual environment over the Internet. NPSnet is a large-scale virtual environment. We can support about 200 to 300 players using Ethernet and T1 links. For the demonstration at the symposium, we're going to be showing you NPSnet playing across Internet. It is the first three-dimensional virtual environment that can actually play in a distributed fashion across the Internet. NPSnet can simulate ground vehicles, air vehicles, and humans walking through the network synthetic environment. The network protocol that we use is called the DIS protocol, the Distributed Interactive Simulation Protocol, which is a Department of Defense and IEEE standard. NPSnet is Silicon Graphics Iris-based. You can run it with a single workstation with one monitor in front of you. You can have multi-channel option on an Onyx and have multiple displays. It runs in head-mounted display fashion. Input devices range from keyboards to spaceballs to flight sticks to fully instrumented infantrymen. You can see here a Kaiser Vim helmet, a fully instrumented upper body suit designed by Sarkos Engineering of Salt Lake City, Utah. We've got an instrumented M16 and a force feedback pedal device. When he pedals this device through the virtual environment, he gets the feeling as if he is moving up or down the terrain, depending on what the actual terrain is. We also have a three-walled rear projection environment we call the walk-in synthetic environment. You can see this soldier in an engagement with another soldier. In fact, it's the other soldier you saw with the head-mounted display. Another person?
We're going to scout out the building to the right. You two cover me while I move up to that destroyed vehicle to the left front. When I get there, you two move up to the vehicle on the right and cover me while I move to the building. Let's go.
NPSnet has been demonstrated at a number of shows. What you see in this particular show is the Association for United States Army Conference in Washington, D.C. in October of '94. We have a Special Operations Command soldier trying to clear a building. He can look out the windows and see the other soldiers involved in the engagement. He can fire out the window. Again, this is networked. Some of these other players are workstations with people on the workstation. Some of them are in the iPort device. We do medical corpsman rescue training. Here he is resurrecting a downed soldier. The human figures in NPSnet are manipulated using the University of Pennsylvania JAK software from Norm Badler's group. There are 76 degrees of freedom in the soldiers, and JAK is an embedded function of NPSnet 4.7J.